In this short series of videos, we are going to go through with one example all of the different definitions that we provided on the graph theory worksheet. We are going to look at this example that we have right here, and we're going to look at the following terms. We're going to look at the adjacency matrix of that graph, the degrees of the vertices of that graph, some various examples of paths within this graph. We're going to look at taking powers of that adjacency matrix and talk about how to interpret the powers of that matrix in terms of the picture that we see. We'll go over geodesics, cut points, and bridges, and then we'll move into some more advanced topics, which would be the line graph associated with this graph, computing the betweenness centralities of various vertices, and computing the Cheeger constant. So the plan is to break this up into three roughly 5-minute videos on each of the columns that you see here, 1 through 3, 4 through 7, and 8 through 10. So let's get started with 1 through 3. Let's look at the adjacency matrix of this graph. So because we have 5 vertices, 1, 2, 3, 4, 5, what we have for the adjacency matrix is a 5 by 5 matrix where the first row is corresponding to vertex 1, the second row is corresponding to vertex 2, and so on, and the same with the columns. And we're putting a 1 in a spot if there's an edge between those two vertices. So we have a 1 right here because there is an edge between vertex 1 and vertex 2. A 0 right here because there is no edge from 1 to 1. And there is no edge from 1 to 3, and similarly no edge from 1 to 4, but there is an edge connecting vertices 1 and 5, and we fill out the entire matrix that way. In terms of the degrees of the vertices, all we're doing is counting the number of edges that contain that vertex, and so we can just sort of walk around the graph and say there are 2 edges here, 3 edges here, 3 edges here, just 1 edge connecting vertex 4 to the rest of the graph, and then 3 edges at vertex 5. Now paths in the graph, there's lots of different ways to represent them, but generally we think of paths as a sequence of edges connecting two vertices. So if we were looking at vertex 1 and vertex 5, one such path would be to travel the edges A, B, and then D, and you would start at vertex 1 and you would end at vertex 5. Similarly, E is a path by itself just from vertex 1 to vertex 5, and so this is something we'll discuss a little bit more later, but ABD is an example of a path within the graph. However, that path is not a geodesic. A geodesic is going to be a path in the graph of the smallest length that it could possibly be. So E in this instance would be an example of a geodesic from vertex 1 to vertex 5, but both of those collections or sequences of edges are perfectly valid paths. Now the last thing that I want to cover in this video is talking about taking powers of the adjacency matrix. So there's a big long computation that's going on here, but if you're not familiar with matrix multiplication, I want to do one little example here. I want to take a look at this entry right here, this red 2 in the final product in the product of these two matrices. Now when you're computing the product of matrices, there's a little procedure that's something that's just way easier animated than explained in mathematical writing. The idea is we're going to come up with this 2 here by doing a sequence of products and then adding all of those products together. And because we're working in the first row, third column of this final matrix, we'll be looking in the first row of the first matrix and the third column of the second matrix, doing the following procedure. Looking at 0 times 0, then 1 times 1, then 0 times 0, then 0 times 1, and lastly 1 times 1. And once we've computed those 5 products, we add them all together, giving us a result of 2 that we see here. Now the procedure for multiplying matrices may or may not be something you've seen before, but what I really want to point out is the relationship that that procedure has with this graph and what it means for us. So if you think about what was happening when we got a non-zero entry in that summand that we just computed, this 1 in the first matrix is representing that there is an edge between vertex 1 and vertex 2. Because it's in the first row, second column. When we're working over here in the second row, third column, that's indicating that there's an edge between vertex 2 and vertex 3. So this product of two ones is saying, yes, there is an edge from here to here, and yes, there is an edge from here to here. And so altogether, we have squared our adjacency matrix, and what we've picked up on is that there is a path of length 2 from vertex 1 to vertex 3, coming from 1 goes to 2 and 2 goes to 3, right here. And if you continue down, for example, when we reach this entry right here, there's a 0 there that would get multiplied by this 1 right here. That's saying there is no path between vertex 1 and vertex 4, which is true, but there does happen to be a path between vertex 4 and vertex 3. And so since we're missing any one link of that process, we don't want to contribute to the sum here with a 1, because that does not ultimately lead to a path of length 2 between these vertices. But then again, we do in the end, because there is another path from vertex 1 to vertex 3 of length 2, and that's first going from vertex 1 to vertex 5, and then going from vertex 5 to vertex 3, right at the end. So each time we get a 1, it's coming about from having an edge here and an edge here. And so this number 2 right here is representing the number of length 2 paths from vertex 1 to vertex 3. And that's true of all the entries that you're seeing in this matrix. In particular, you're seeing the degrees of the graph right here along the diagonal, because it's telling you how many ways you would have to leave that vertex and then come right back. Leave that vertex and then come right back. So that's a useful property of taking the square of an adjacency matrix. And in fact, this trend continues as you take arbitrary powers of the adjacency matrix. It will, if you were taking, for example, the cube of the adjacency matrix, it would be telling you how many length 3 paths there are in the graph between one vertex and the other.